And we are moving on with page 39. It's all about EMR, energy waves. EMR stands for electromagnetic radiation. Electromagnetic radiation, or EMR, is a series of waves that have different energies. There are several parts to a wave. We're only going to talk about two of those parts, but there are others. The crest is the highest point of a wave, and the trough is the lowest point of a wave. So looking at this diagram here, this is a crest right there, that point, or like this point right here is a crest. Or down here at the bottom, that's a trough. Or down here at the bottom of this one, that's a trough. And that's true for all waves, like not just energy waves, but any waves, sine waves and cosine waves, which you'll eventually talk about more in your math classes, sound waves, light waves, even ocean waves. The high part is the crest, the low part is the trough. And the distance from any point on a wave to the next equivalent point, like from crest to crest, that distance is called a wavelength. So like this distance right here is a wavelength of the wave, or from this trough to this trough. That is a wavelength. And if you took out a ruler and measured these, you would see that these were the same length as each other. This is a part of the unit where we're going to start introducing some math, and that means we have to talk about some variables and definitions of things we're going to do math with. So we'll start off easy with wavelength, which we already just discussed. Eventually, and we'll come back to this, but we're going to learn that our variable for wavelength is a Greek letter called lambda. It looks like this. I think the reason we chose lambda, or at least this is what I tell myself, is that if you draw like a bunch of them in a row, it starts to kind of look like ocean waves, you know, like, dude, maybe that's dumb, I don't know, but wavelength, we use this Greek letter, lambda, and our definition for wavelength would be the length of a wave, which we measure as the distance from crest to crest, or trough to trough. Excuse me, crest to crest, or trough to trough. We can also talk about frequency, which we abbreviate with a lowercase f for our variable. Frequency is how many times a wavelength passes by in 1 second. So waves are always like moving, and let's say, you know, maybe you're standing like right here, and the wave is going by you, it's moving past you. Every time you counted like crest to crest, there's one wavelength that goes by, or another crest to crest, another wavelength goes by. Every one of those you can count that goes by you in 1 second, that tells you what the frequency of the wave is. And that means if the wave is short, if that length is short, you're going to get more of them going by you in 1 second than if the length is long, which means that the lower, or I guess we could just go with smaller the wavelength, the bigger the frequency. Shorter waves, more of them are going to pass by you. Another variable we have is the speed of light. And eventually we're going to use a lowercase c to stand for speed of light. Electromagnetic radiation waves always travel at 3 times 10 to the 8th meters per second. So that's, again, 3 times 10 to the 8th. That's going to be like, whoops. Let me try that again. Yeah, 30 million meters every second. And our, basically, we're going to find that c is a constant. The speed of light is a constant. That's why we chose c, because it's a constant. It is always going to equal 3 times 10 to the 8th. Every time you need to plug in c to an equation, you're going to plug in that same number, 3 times 10 to the 8th. Or in your calculator, you would type it 3e8. Next, we need to make sure we talk about energy. Our variable for energy is just going to be a capital E. Energy is the ability to do work or transfer heat. We're going to, again, have a whole unit about energy when we end the year. And energy is related to wavelength and frequency, where basically if you have high frequency, waves, those are going to be high energy waves.
Mm-hmm.
And our last variable we need to talk about is called Planck's constant. It's named after a guy, Maxwell Planck. Eventually we're going to show a lowercase h as our variable for this number, Planck's constant. It is always equal to 6.63 times 10 to the negative 34th joules per second. We're going to talk about joules some more later, but basically anytime you plug in h to one of our mathematical equations, you're going to plug in this number right here. 6.63 times 10 to the negative 34, or just 6.63 e negative 34 when you type it in your calculator. We're going to see some equations that use Planck's constant that tell us that when we have a long wavelength, or I guess I'll just stick to bigger and smaller, a bigger wavelength is going to be a smaller amount of energy. So looking back at these pictures, we can label a few things. This one with the small wavelength has a high frequency. This one with the long wavelength, the big wavelength, is going to have a low frequency. And similarly, this one with the small, short wavelength here is going to have a high energy. And this one with the long, big wavelength is going to have a low energy. So wavelength is going to go opposite of both frequency and energy. And when you're done writing that, you can turn your page. Let's look at page 40. The electromagnetic radiation that we encounter in the universe exists on a spectrum. There's a lot of different types of electromagnetic radiation. There are radio waves, like, yes, the radio you listen to in your car. Microwaves, yes, like the stuff that cooks your food. Okay. Infrared waves or infrared light, which is, you probably have encountered it by if you're watching TV and you see someone using like heat vision goggles, night vision goggles. Those use the infrared spectrum, or just your remote control to your TV uses infrared light. If you have an automatic garage, most automatic door garages have a little laser type thing that if something's blocking it, the garage won't open or close, to prevent people and things from getting crushed. And that's actually not a real laser. That's usually infrared light as well. There's visible light, which is this tiny piece of the spectrum that human eyes have adapted to see. And there's ultraviolet light, like a black light, that they use at clubs, I guess. You're too young to go to clubs, but I'm sure you know what a black light is. And, humans can see within what we call the visible spectrum. But there are other organisms that see in infrared and ultraviolet that they've adapted differently. So there are some, like reptiles, that see closer to the infrared spectrum than humans do. And there are some insects that use the ultraviolet spectrum instead. What stuff looks like to you under a black light, that's how like bees see that same stuff all the time in normal light, because their eyes have adapted to use the ultraviolet part of the spectrum instead. X-rays, yes, like when you break a bone and you go to the doctor. Gamma rays, people tend to think of this as, if you've even heard of these, you think of the Incredible Hulk, but gamma rays in real life are more radiation than anything else. They don't turn you into a giant green rage monster, they just give you cancer and you die. But yeah, these are the main parts of the electromagnetic spectrum, electromagnetic radiation spectrum. For lack of a better word, you can kind of think of all of these as different types of light, because this electromagnetic radiation all moves at the speed of light. But we can see that radio waves are very long, and as we move through the spectrum, the waves get very short. You can remember which side of the spectrum is the long side if you think about radio waves. Radio towers are like these really tall towers, right? And they have these blinking red lights at the top. I think I have a red somewhere over here. Hang on. But it's these big metal towers, and they have the blinking red lights at the top so planes don't hit them, and they you know what I mean. But those radio towers are that tall because they have to be the same height as the waves that they put out to transmit data to the radio in your car. So their wavelength, and I didn't draw this super well, but their wavelength has to be the same as the height of the tower, whatever wavelength their frequency is supposed to broadcast at to your radio. That's supposed to be the same height as their tower. So that's really, really long waves on the radio end of the spectrum. And we can see a relationship between these long radio waves. They have a relatively small frequency, only 10 to the fourth, versus these really short electromagnetic waves like gamma rays that are very short. They have a very high frequency, 10 to the 20th. And we have a mnemonic device for helping us figure out what order these go in: radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. The mnemonic device we use is red Martians invade Venus using X-ray guns. Red Martians, red for radio, Martians for microwave, invade for infrared, Venus for visible, using for ultraviolet, X-ray for X-ray, and guns for gamma ray. So that's how you can remember what order they go in. And then the visible spectrum, in the center here, the visible spectrum has its own order it goes in. And we've kind of set it up more down here. It's red, then orange, then yellow, then green, then blue. Hold on a second. That's this one, blue. Then indigo, which is sort of similar to blue for most people. A lot of people don't really know where the line between blue and indigo ends. And then finally violet. Some of you may have seen where I was going with this. Yeah, these are the colors of the rainbow. And we can have a little mnemonic device to remember their order as well. We call it Roy G. Biv, like it's somebody's name, to remember what order the visible spectrum goes in as well. You need to know both of these orders. You need to know red Martians invade Venus using X-ray guns for radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. You also need to know Roy G. Biv for red, orange, yellow, green, blue, indigo, and violet. You need to know that order. You also need to know where they fall on the wavelength side. So for both radio, microwave, infrared, so on, and for Roy G. Biv, we've put them in order for you, where the big wavelength, or you could say the long wavelength, is on the left, and the low or small frequency and low and small energy are also on the left. Whereas the smaller, you could say short wavelengths are on the right, and the high frequency and high energy are on the right. So knowing that, let's look at a couple questions to kind of compare. Which has higher energy, UV or X-ray? Well, if we look up at our chart, UV versus X-ray, I know that high energy is going to be the one further to the right, which is the X-ray further to the right. So higher energy is going to be X-ray. Which has a lower frequency, I know that frequency is going to be low on the left. So X-ray versus gamma, which one's further left? If I look up here, X-ray versus gamma, X-ray's further left. That's going to be a lower frequency. Shorter wavelength, I know that my wavelength is short on the right side. visible or microwave, so the one further right is going to have the shorter wavelength. Visible versus microwave, the one further right has the shorter wavelength, so that's going to be visible. And lower energy, blue versus yellow light. Again, low energy is going to be on the left side. So blue versus yellow, yellow's further left. Yellow is going to be a lower energy. And when you're done writing that, you can flip to the next page, page 41. And on this page, there's an activity for you to do. There's a link here for you to follow. Oops, sorry, right there. And you're going to go to that link. You're going to peruse the website, fill in this chart with the uses and dangers of each one of these kinds of waves, and answer the questions at the bottom. This is going to be for a stamp, so real quick, let's go to your stamp page for Unit 4. I believe at this point it is either the 16th or the 17th, depending on if you're an A day or a B day. And page 41 is going to be what you're getting a stamp for. There are more things to do today after you finish that stamp, so Ms. Woodlock is going to tell you how much time you have, and then we're going to move on within a different video.